kitten that was making sounds in the yard and lost track of time. Let me hop on to the various mediums and we'll get started. Sorry about that. Let's get on Zoom. I think everyone left Zoom. That's unfortunate. Okay, we're on Zoom. Let's share the screen. So that everyone can see it on Zoom as well. What a crazy time. Okay, where is Zoom? Zoom, share screen. This. Okay, let's start rolling. Oh, and then let's get on Twitch on the iPad. What the heck? Come on, Twitch. There we go. Why does it think I'm offline? No, I'm online. Okay, awesome. Cool. Okay, I think we're just under the 15 minutes, after which everyone bails because the professor didn't show up. But we have 0 viewers. Let's take some time for viewers or attendees on office hours. Man, you're a little late. No one shows up. That's okay. Let's make a Canvas announcement. Okay, Canvas announcement made. We have a couple people streaming in on Twitch. 1 extra participant on the Zoom. Awesome. What else do I need to do? Oh yeah, I need to tweet. Oof. Okay, let's roll. Okay, any questions about reverse engineering? Someone's saying that they ran into a problem on level 14, the disassembler for Yan 85. It's not easy. Someone's stuck on level 9 testing. Okay, so a question for level 9 testing. How can I use pwn.debug to check what happens in the final Stern comp? Let's take a look. Of course, my level 9 is going to be a little different than your level 9, but we will do our best. Let's take a look. Okay, that's my binary ninja session from earlier. Let's take a look at level 9. Level 9 testing 1. Spin it up. We'll download. Let's open it up in Binary Ninja just for fun. All right. So it's this is the wait. What the hell? Hold on, my OBS is misconfigured. Ay, ay, ay. One sec. That's my OBS. This is where the browser should be. There. Awesome. Okay. Perfect. Sorry about that. So, this is my level 9 testing. Basically, if we just kind of scroll through it, of course, there's the normal prologue, normal introduction to the challenge. And then here it's calling socket, calling set sock up, H2NS, bind, listen, accept. And this looks like a typical network server, right? And then it calls malloc, read again. And then it starts doing all of these crazy manglers. Let's take a look at it in the decompilation. Here, I guess. So it's creating a socket, listening on TCP on the internet, does some socket operation stuff, and then it does this hex to host to network short. Sorry, if we display it as an unsigned decimal, this host network short 48474 is wow, this decompilation really is struggling a little bit. Is most likely the port. If you look at a socket tutorial. Sorry, I have to blow my nose. It's allergy season and my allergy meds haven't kicked in. Sorry about that. If we look at a typical network socket server tutorial, we can see we'll see something along the lines of set your well, let's take a look. Let me show you. Socket server tutorial C from my alma mater, RPI, undergrad institution, and if we search H2NS, the port is set like this, right? Port number. Cool. So H2NS takes something that is generally little endian, converts it to a little endian because it's the host endianness, usually little endian, converts it to big endian, which is the network endianness. But that is not as important as the fact that that's the port. All right, so we're going to listen on this port. Then we're going to do a whole bunch of stuff, and this is basically unreadable in the decompiled output. And then we're going to mine memcomps, but same sort of concept. It'll memcomp hex 14 bytes between my input and the expected result. So the question is, how do we use pwn.debug to see what actually happens in that final memcomp? Let me log out of this. SSH in. And do I have pwn.debug configured here? No. So I'm just going to actually copy the the challenge out. All right, let's run pwn.debug in tmux and open this baby rev level 9 testing 1. Okay. Let's run. So it starts out and it is waiting for me to send the license key. Here's another window in tmux. If I connect with netcat to localhost, that's my local machine, and the port from that the binary specifies 48474. Okay, I connected. I type the key, and it says wrong. Okay, awesome. So another thing, by the way, I can do if I had the mouse mode is switch over to, you know, this pane here and do the connection from there, but I don't have that part installed locally, and I don't know how to do it in tmux. Oh my god, guys, please, somebody, if you don't see the terminal, yell at me in Zoom. Yeah. All right, let's start over. So we're going to create a new session for tmux with GDB in opening this testing one, right? Level 9 testing one. Hit enter. All right. So we started out here. We are going to hit run. All right, we're ready to receive the license key. And now, is there a tmux expert? How do we in tmux move to the right in a split pane? Control B arrow key. Okay. Oh, amazing. All right, so here we're going to import pwn. No module named pwn. Let's install pwn tools real quick. Okay, import pwn. This works. We're going to connect to the this port right here, 48474. Oops. What's going on? God damn it. Okay. Something is wrong. Okay, Python went crazy. All right, we're not going to use that Python shell. We're just going to use this, and we're going to do the netcat that we did before. Localhost 48. Sorry. It was because I was outside hunting down a screaming kitten that is either in my yard or my neighbor's yard. Haven't found it yet, but after office hours I'm going to go back out and try to find it again, because it sounds like it's pretty sad. All right, anyways, we connect up to the port, we give it our input, and then when we come back it says wrong, no flag for you. Okay, so now we want to see what went wrong, what happened with the memcomp, but stern comp works in a very similar way. Let's take a look. So now we can do break at memcomp. Okay. And we run it again. Connect up. Send some stuff. And too much fancy shit, man. All right. So memcomp is obviously, I don't know what pwn debug is doing here, but let's go back to the binary and fix up, figure out where to break specifically. So here is the memcomp. Let's take a look at the disassembly where that memcomp is. The memcomp, here's checking the received license key, and here is the memcomp at 15FF into the file. So that's where we're going to break. God damn it. That's where we're going to break at. Instead of this thing, we're going to break at rebase OX1FF. Wasn't it rebase? This is frustrating. Oh. No, yes, sorry. Sorry guys, I'm discombobulated. So we break in the file where that memcomp will be called. We continue and it doesn't happen. Let's run this again, just in case I was already too far along. All right, we connect up, send something. Okay, now we hit the breakpoint. And this is a normal function, so of course RSI is, or RDI is the first argument, RSI is the second argument, RDX is the length. So we can print out RDI. So first thing we can see is that something sorted this, but of course this is my level 9 testing one. Yours might have different manglers. And then if you look at RSI, this is the result. So then we can just try copy and pasting this. Actually, first thing we should do is figure out how much padding got read in. We can actually see this from the decompilation. If you look here, let's go to decompilation. We read into this buffer, or from the file descriptor that represents our connection, into some garbage buffer 16 bytes, and then we read into the real buffer hex 14, which is 20 bytes. So we have to pad with 16 bytes and then put in 20 bytes. Let's take a look at how close we can get just by copy pasting that. So let's do IPython here, import pwn, and then we'll just write a little program here in IPython, pwn.remote localhost this, and then we'll do r.write, and we will write 16 A's plus this expected result. I'm sure this won't be enough. There's probably more mangling, but let's see. So let's run. We do this. We're at the breakpoint, and here's the expected result again, and here is what we have. And it actually looks pretty good if we hit correct. Boom. That was way easier than a level 9 should have been, but I probably got fairly lucky with the manglers. Okay. Awesome. That's how to inspect arguments to a functional. I'm not sure why break memcomp didn't work. That should have worked, and it would have worked in vanilla GDB. I'm guessing pwn debug screwed something up. But you can always break at this place in the binary that it calls the function in question. So, oh, awesome. That solved that student's problem. That's great. Okay. Any other questions? Someone has a question on the disassembler for level 14. What's the question? All right, so we have a specific question about the disassembler for level 14. Is it better in an email? If it's very specific, then probably it's not. All right, so let's take a quick look at 14 testing, just kind of on a high level. So let's close the other tabs. All right, 14 testing. Here we go. Let's take a look at it in Binary Ninja. Um, 14 testing is the first level of the interpreter, right? And this interpreter is for the Yan 85 architecture. Never been seen before until this class. And the general idea is to convey how to disassemble or how to reverse engineer emulator protected code, right? So a lot of code nowadays in digital rights management software and so forth, and anti-cheat and obfuscated code in general uses VM obfuscation. If you end up having to reverse that, it can be quite a challenge. And I implemented a small architecture with a simple virtual machine that can do operations and call system calls and so forth, right? It has 8 instructions, as you can see, and an interpreter loop that is pretty basic, just loops around, interpreting instruction after instruction. Then it interprets each instruction, and so on. The nice thing about this architecture is that it is a randomized architecture. Excuse me, gotta blow my nose. Man, seasonal allergies are tough. All right, it is a randomized. It supports instruction set architecture randomization, so everyone gets a slightly different randomized architecture in terms of what instructions map to what bytes and so forth. All right. So how do we reverse engineer this? Well, one, you have to reverse engineer each of these handlers to understand what they do, whether dynamically or statically. And two, you have to reverse engineer the virtual machine program, the program that runs within the virtual machine, not the emulator, but also the program within the virtual machine. Because if we run this, and we SSH in here, and we run this guy. Thank you for letting me know. Can't see my terminal. Okay. If we run this, you know what I should do? Here, I should put a terminal on the top right, just so people can see something. Yeah, maybe I can automate that to switch scenes automatically. That's a good idea. Anyways, the it asked me for this for a key, and then I put in a key just like the other key gen things, and then it says incorrect. All right, a couple of interesting things. I didn't type this. This is the last some amount of bytes of my input here, because evidently, if we strace this guy, and I put in a bunch of stuff, it only reads 8 characters. So the rest is left in the standard in pipe, and the shell ends up reading it. And that's fine, whatever. But now we know that the key is 8 bytes in length. But a couple of questions remain. One is, where does this whole enter key thing come from? If we look at the strings in this file and look for enter, it's not there. Right? So this tells us that the string is printed in some special ways, not just a string constant in the program. And in fact, I can tell you that that is absolutely correct. It is not a string constant in the program. It is printed by the code running inside the virtual machine. So you need to reverse engineer the code running inside the virtual machine. The way we do this is, of course, we look at, we can see that interpreter loop calls interpreter instruction, which is kind of the dispatcher to the individual instructions. This interpret loop, of course, takes some arguments, right? Or the interpret instruction takes a couple arguments. Interpret loop takes, it looks like, one argument, just one. So I don't see an RSI being accessed anywhere in the function at all, actually. It saves it to this var20, and then this var20 has a bunch of stuff done to it that we don't even have to reverse to get this high level of understanding. But basically, interpreter loop takes one argument. We can, based on the name, that it's a loop that loops and interprets things, the argument seems to be what it will interpret. And in fact, if you look at main, which is what calls interpreter loop, interpreter loop is called with RAX, which is this variable pointing to RBP minus 418, this var 418. Var 418 is passed as the first argument to memcopy, the destination of a copy, where the source is a variable called vmcode. So obviously this is the code of the virtual machine, of the program running inside the virtual machine. If you take a look, here it is. This is the virtualized code that does the license key check. Pretty cool stuff. All right. One thing that you can see right away is enter key. ENTERKEY. Right? That's where enter key comes from. The other things you can actually see just from scrolling through is CORRECT. So question on how I got there. I started at interpreter loop. That was a question on Zoom for those confused why I suddenly stopped and started doing something different. I got there, I looked at interpreter loop and I saw interpreter loop takes one argument and does something. So the argument is what it should be interpreting. I went up to main, which is what calls interpreter loop, and I saw that the argument it takes is this buffer on the stack. The buffer on the stack is the destination of a memcopy, to which the source is this VM code, and I double click on that, and this is the code this is the virtualized program that runs inside the virtual machine. Okay, and there's, just by looking at it, you can already see a lot of things. I pointed out correct just now. No, wait, where did it go? Yeah, here's correct. Here is incorrect. Incorrect. Right, so this program obviously encodes whatever the logic is to ask for the key, to check the key, and to print correct or incorrect. And this is the code that you have to reverse engineer. Because reverse engineering this virtual machine is actually pretty straightforward. There are enough symbols, all the function names are there, all of the variable names are there. or many of the variable names are there. And you can, you should of course understand what each of these instruction handlers is doing conceptually, like what an im versus a sys instruction is. But this is fairly easy. If you look at sys, you can see that sys calls open, sys calls, let's look at it in a graph. Sys can call open, sys can call read, sys can call read. There are two ways that sys can call read. Apparently sys can call write, sys can call sleep, and sys can call exit, right? So there's, this seems to be an instruction for interacting with the system, right? You need to understand the other instructions and be able to actually reverse engineer, understand the encoding of the instructions. What just happened? And be able to reverse engineer. I think I ran into a bug in Binary Ninja just now. Yeah, that's a bug in Binary Ninja. That's annoying. Here, let's just refresh this. And yeah, there we go. You have to be able to disassemble and reverse engineer this code right here. Cool. So I'm saying on Binary Ninja and Ghidra, one of the interpret loop options has an unclear opcode. Yeah, go for it. Explain to me. Yeah, so there's the question has to do with basically there's confusing decompilation in some of the handlers. So my advice, this is not very readable or understandable. When there's complex code that deals with bits, most decompilers will produce something that is very, very confusing and is not very useful. Look at the disassembly instead of the decompilation, especially for these individual handlers. This will there's more to read here, of course, but it will give you the actual correct information. Awesome. How's everyone liking Yan 85 in general? So the question is that this is a common approach. Is this a common approach to prevent reverse engineering? This virtualization, or not virtualization? This obfuscation via a VM. So for a while it was extremely popular in obfuscation in DRM, right? There were a couple of digital rights management approaches that would that implemented the meat of their checks in a virtual a VM protected chunk of code. This is slowly moving into dedicated hardware, or like the trusted computing platform stuff on your phone, for example, TrustZone or TPM on desktops. We're slowly seeing digital rights management move closer to that realm, especially with the rise of processor features like secure enclaves, which give you a secured, inaccessible, completely private area for a part of a program to run. This is perfect for digital rights management, right? This VM code is moving now really toward obfuscation. So if you look at even commercial obfuscation products such as Themida, it's a program that'll obfuscate. Just you give it a program and it'll obfuscate it so that it's harder to reverse engineer. That is this is the general approach that they use among other anti-debugging and anti-reverse engineering approaches. As of a couple of years ago, for example, Spotify was protected with this technique with VMing, not with Yan 85 obviously, but with slightly different products, specifically I think Themida. So there's a question on the disassembly is might be hard to understand, right? So for example, this one. Now this one's pretty straightforward. Let's take a. All right. So there's basically a question, and some of these in this, for example, handler loop. There's, for example, this test ALAL and then JNS. What is JNS? There are two ways that you can figure out what is going on here. One is you can run it dynamically and see when it'll take this jump, right? The other thing you can do is look up what JNS means. JNS means jump if not signed. It means the sign flag has to be 0. Test ALAL will set a bunch of flags. The sign flag is the most significant bit of a number. If it's set, then the number is signed. It's negative, right? It has a negative sign. Of course, as we talked about with 2's complement, it's only signed when it's being operated on by signed operations. Otherwise, it happily can be interpreted as an unsigned value as well. But this was some compiler optimization. Instead of a JE just like this that checks the 0 flag, they instead checked the sign flag. This is a signal that in my version of level 14 testing, this jump will only be taken when the sign flag, when the most significant bit of AL, which is the least significant byte of EAX, is 0, right? So this really is checking for the most significant bit of AL, and if that bit is set, then it executes interpret sys. So in my version of Yan 85 on level 14, Testing 1, interpret sys has an opcode of OX800, or sorry, OX80, which is 10000000 in binary. But in yours, it'll likely be different. But compiler optimizations can cause compilers to output really weird types of checks here. So you might have to dig into, for example, these sort of quick references and then understanding what the sign bit is here. It's the highest bit of whatever result. And in test, when using test, that operation is an AND between the arguments. Any other questions from anybody? Is everyone all... is there a good way to input non-printable ASCII in testing 14? Yeah, absolutely. Pwn tools. With Pwn tools, you can input whatever you want. Yeah, so you might notice level 14 is different than the others in that we don't ensure that things are printable. My advice to input non-printables with Pwn tools. So here we are on the terminal. I remembered. Again, we can do pwn.remote, pwn.process to launch this. What's going on? Process to launch this process. Okay. Boom, and then we can do r.write, and we can write whatever we want. This writes a bunch of non-printables. I mean, some of these are printable, but this is basically a byte with a value of 0, or 1, 2, 3, 4, 5, 6, 7, 8, and then we can just read, and we can see that it got the key, and then it told us it was incorrect. Yeah, it's much easier to use Pwn tools than to do this in Bash, especially as we get more and more, as we get deeper and deeper into the course, especially with the memory errors module coming up, you're going to want to embrace Pwn tools. All right, there was a question. Do we have a good way of going to GDB and setting breakpoints and piping in unprintable characters to the process? Yes, so there's a couple possibilities. One is you can use... so Pwn tools has a GDB module that it can I always forget debug. Yeah, so this Pwn tools.gdb.debug will launch your process. Let me actually start up a tmux. And then we'll, hold on. Let me just reset my GDB init configuration. Okay, perfect. And this is Connor's magic configuration that allows clicking. Awesome. Okay, so check this out. Here, we can import pwn GDB debug and I'm sure easier ways to do this, but this is the way that I don't see any immediate reasons why it should break in this configuration. So we do a debug of the no, Connor, this is gonna work. All right, we launch the program in debug mode. Oh my god. Connor, do you see what happened? Okay. Okay, but yeah. All right, so here we go. I launch IPython. Import pwn gdb.debug. There's a way to do it non-intrusively. I always forget. All right, here we go. We ran it, and it basically, even this is kind of ugly. It just creates new panes. Yeah. So here it launched up GDB. It gave you a pwn tools tube. I should have done this, and you can happily interact with it. Hold on. How do you get it? Connor, did you custom configure pwn tools to do that? I see. Oh, because it's the default GDB config. There's a. All right, let's do this. No, this is actually the opposite of what we want. So okay, if you have a big enough screen to handle this, launch up tmux in IPython, import pwn gdb debug. /babyrev and so forth. And then, of course, we're running. Here we are. Connor, do you know how to shrink this? Oh, wow. This works. Huh. Is this normal tmux behavior, Connor? This thing is pretty advanced. They haven't been idle for 14 years. Dang, screen does not have this. Let's put it that way. I'm very impressed. Okay, anyways, so you can see we launched it in GDB and it's created all the GDB things, and now we can interact with it here, right? So we can if we do continue, we can say, you know, enter. As we see, it says enter key, and now we can write. First of all, we can break. We can break at I don't know. We can do a catch syscall write. So this will catch anytime that the process writes, and then we will write to it. And let's continue. Then we'll write to it, you know, some input, including non-printables. Okay, and here we are at catch point. It is trying to write something. Let's see what it is writing. Sorry, that's file descriptor. It is writing incorrect. Right, so we launched it in GDB from pwn tools, and it automatically created our whole insane pwn tool setup here, or insane pwn debug setup. Awesome. So the question is, can we break at main? That's more or less what this already does. So if we do this, yeah, when pwn tools launches GDB, it'll automatically break at the start. And specifically, let's see, is it breaking at start or at main? Easiest way. This looks like main. No, this is start. Yeah, okay. And then now we're executing through the loader. we can break main, continue. Here we go, never at main. So it breaks just at the start point. Okay, another way, if you don't want to deal with pwn tools and tmux and all of this hipster stuff, is this. You run GDB. Oh no. Okay, well, whatever. Even with the fancy stuff, run, and there's a reason you learned about FIFOs. You can redirect some FIFO here. Of course, you have to create a FIFO. Okay, and here home CTF. If you do, oops, I just ran GDB. GDB baby rev here, awesome. And now if you run home CTF some FIFO, and of course it started up and is now waiting for you to write something. So for example, you can cat some FIFO. It's waiting for, hold on. And you can cat to some FIFO. Okay, what's going on? Oops, my bad. For some reason this didn't flush. So let's run this. Okay, now it's gone. Let's run this again. Pwn debug is too much magic, man. Okay. So we start with an input being redirected from the FIFO, just like in whatever level the FIFOs were in. And now whenever it will read input, it's going to wait for you to write your input into the FIFO. So now you can even use echo. By the way, another way, straight on the shell, if you really want to use the shell to write your non-printables, you can do it like this. $, single quote, easier. That's shorthand for essentially the same thing as this. Echo -e. Don't forget -n so you don't write a new line. And here's this. You put in the ASCII values and it writes it all out. And then, of course, we can write this to some FIFO. And it read it and happily told us it was incorrect. Probably pwn tools, generally speaking, is much easier. Any other questions? Yeah, so we have this question on number 14. Number 14, yeah, we have the VM. This is this guy with all the interpreter, interpret this, interpret that, write memory, read register, etc. And we have the actual code inside the VM that we need to understand. Yes. This is the actual code that does the check. Yes, exactly. This is the program. This is the program that checks the license key you provide. And this is the program that interprets that program. And this actually concept of a interpreter that interprets some sort of binary code that is not native to the architecture. Another name for this is bytecode. It is just some code compiled to some bytes that you interpret. Bytecode is used in Python. When you run a Python program, when you do import pwn to get pwn tools, what is happening is that Python code is being compiled into bytecode. That bytecode is not Yan85. but it is Python bytecode. Python bytecode actually has a specification. In fact, let me show it to you. This is completely off topic, but we're going to do it anyways. So here's IPython. Let's create a function that takes a and prints a plus 1. Okay. Thank you for telling me that. Here's my terminal, ASDF1. Okay, that's my function, right? If we do ASDF, functions are just objects in Python, and we can do that. Code. This is a code object. And if you look at the actual, where is it? Code. Okay. This is Python's bytecode, right? This is the binary code that defines this Python program in very much the same way that, I mean, it's a different architecture, doesn't like hinting or anything. But it conceptually similar to the VM code here. So this isn't even something that is completely crazy and just seen in secure critical code like digital rights management. This concept is seen everywhere. Interpreters are some of the most popular languages that we see are interpreted, and we'll actually see different takes on like ways that interpreters can be faster using just-in-time compilation and so forth later in the course. Oh, yeah. So actually, Python has a, what is going on? Okay, here we go. Python has a disassembler. So if you can do dis, and I will have to disassemble the code. Dude, what is this mouse thing doing? What? Okay, fine. ASDF.code.co code. Is it just disassemble on the code object? There we go. Okay. So here is the disassembly that someone wrote for Python code. And here you can see the way that ASDF works. It loads a global called print. It loads a variable a. It loads a constant 1. It does an add. And then it calls the function that is a stack-based virtual machine. It calls the function that's a bit higher on the stack, which is print. Pretty cool. Cool. Any other questions? Let me take a look. There are a few questions that makes me a little worried that that people have like given up. How many solves do we have on 14? Why is this broken? Gosh darn it. How many solves do we have on 14? 36. But more and more people are, yeah, this is the patch me's. Okay. All right, we'll hope for the best. Okay, someone is asking on Zoom, may I ask about older challenges? Yeah, absolutely. If you have no other questions, let's go on to older challenges. Okay, baby shell level 5. Let's take a look. Okay. Baby shell level 5. Oops. Okay. Baby shell level. What is going on? Connor, your Tmux mouse thing. This is your Tmux mouse thing somehow. It is. It's destroying my terminal. Okay. We're back. You don't use Tmux? Wait, what? So Connor's telling me that he uses Emacs instead of Tmux. I don't know, man. That's like saying you use Notepad instead of Tmux. It makes no sense. All right. Anyways. Okay. Level 5 in Baby Shell. For those that are catching up on the makeups. It's an interesting sort of level. It reads in your shellcode. Of course, you know, you can give it up to 4,000 bytes. So, you know, likely that's not going to be a challenge to fit your shellcode. But it makes sure that your shellcode does not have any syscall or sysenter instructions, right? And the teaching challenge says, hey, you can get around this because your shellcode can provide you can provide shellcode that doesn't have any syscall, sysenter, or int instructions. These are the instructions you need to trigger system calls. But you can have your shellcode modify itself to create these instructions, right? If the if we strace this, we see that it reads in some stuff here. Okay. Where did it read it into? It read into a this page here that is mounted, or that is mapped, read, write, and executable, and then it never fixed that. So the place where your shellcode is still readable, writable, and executable, and you even know where it is. So it's nice and simple. But even if you didn't, you could use instruction pointer relative rights to modify your shellcode. So the goal here is modify your shellcode to execute a syscall. Does that help? All right, let's go through one example of how we might modify shellcode that just kind of on our let's see. Let's look at exit.s. So let's say we didn't have the syscall filter. I'll leave it up to you to generalize this. But here we have shellcode that moves 16 to REX. This is the exit syscall number. Moves 42 into the syscall and then runs syscall, right? So this into the argument and then runs syscall. So this will exit 42, right? We can assemble exit.s, and when we run exit.elf, just exits 42. Okay, let's do one more thing. Let's actually, instead of assembling it this way, let's enable a writable text segment. So this will be how we assemble it. Okay, so now it's the same. We strace exit.elf. Okay, we can object dump it to oops, -j. I don't know where that came from. Here is our shellcode. Okay, let's say we wanted this to be different than 42, but we wanted to return 43. So 2A is 42, 2B is 43. But 43 was not allowed in our shellcode, right? What could we do? We could, at runtime, increment 2A to 2B. Let me show you what I mean. Let's add a label here so we can refer to it easier. Our modified target. And here, what we're going to do is increment some byte of modified target, right? And what is that byte? We started at, this instruction starts at 401007. And this byte is, this is 401007. 401008, 401009, 401008. Of course, that's just where it is in this statically linked ELF. When we actually are running shellcode, it's going to be somewhere else in memory, like in that 1337000 that we mapped. What we're going to do is just do the start of this instruction plus 1, 2, 3, right? The start is in this modified target, so you can do this. And we are good to go. Say byte pointer to specify that we just want to increment that 1 byte of memory. And let's try compiling this. Now let's see what happened. Oh, oops. Exit.elf. Okay, so now we have a slightly more complicated thing. We increment the instruction pointer, which is pointing to the next instruction, plus 7 in memory. So this as DA plus 7 is going to be E1, E2, E3, E4, evidently. And this is what we're going to increment. Let's step through it in GDB. We'll break right at the start. Okay, run. All right, here we go. We're at the start. We're about to do this increment. Let's take a look at, this is what will be incremented. Let's take a look at what is there right now. Wait, this is the wrong thing. This is the correct instruction. But if you see, if you do this incrementing, so let's this is the next 10 instructions we'll execute, this incrementing, and then we move the syscall number, and then we move this the exit code into RDI. We step. Let's look at the, oh, here's the next couple of instructions. Nothing happened. Hold on. All right, one second. I need to disable pwn debug. This is too much. Okay. Let's break at start. All right. Here we are about to modify RIP plus 7, which is OXC7. So we got the wrong location. Let's see what we actually want to modify as an offset from here. So this is 48 C7 C7 2A. So we're one off. So if we step this instruction, now we've done the modification. And I don't see the incrementing happening. Is there some weird... Oh, interesting. It exits 0 instead of exiting. Oh! Sorry, we forgot +3 here. All right, we're 3 bytes into the thing. Now, let's do this. And if we S-trace it, boom, 43. Cool. We might run into some weirdness if we GDB this. Break at start. Okay, here's the shellcode. We step. It does not show us this as having taken effect. My guess is it has it cached. The GDB itself has it cached. Yeah. Because this, if you look at our DI now, 2A. What? Exit code 052 in is 42. But if you S-trace it, interesting. It's 43. Interesting. Okay. GDB messes things up in terms of self-modifying code. This does sound insane. But look, I compile this. Now obj dump tells us that it's gonna move to A, but of course this will change modify target +3. So this is modify target, or the byte at modify target, +1, +2, +3. It will change the binary, the byte at this memory location, so that by the time it executes, it will be something else entirely. It will actually be not 2A, it's going to be 2B, which is 43. If we S-trace it, we can see that this is what happens. Exited with 43. If we do GDB, and we run, oh, if we do GDB and we run, it. This is in octal. GDB is old enough software to be using octal in many places. You can see that that is 43 in decimal. If we break, run, and continue, it breaks the self-modifying code. Holy crap. That's insane. Yeah, it must be. Maybe this is what happens only in no, but I'm not single stepping. So I'm honestly at a bit of a loss. All right, let's do GDB self-modifying code. So GDB does modify code itself when it sets breakpoints. The way that it does it is for software breakpoints is by putting CCs in there, int3 instructions. But this is a different. yeah, I don't know. It's very interesting that GDB is a bad way to debug this. That's pretty cool. But does this help to understand how self-modifying code works? Awesome. Seems so. Cool. So that's kind of the magic thing. I mean, you can imagine that there is, some bytes. You can do the same thing for syscall as well. I mean, you can also just write in completely new bytes. For example, this is up somewhere. I did a. This is the little endian keyword of the instruction, right? So if we move this into RBX, and then we move into this whole thing, RBX, this is the same thing. In fact, here we can do 41, hex 41, which is 65, and this will return 65 because we're modifying this whole instruction with a different encoding of it. Actually, this part is actually part of the syscall, so that's already a big hint. All right. And now if we strace it, exits with 65. So rather than increment, we can just write shell code into our what's it called? Into the buffer. Cool. All right. Thank you for calling into office hours. If you have more questions, hit up help on Discord or send us an email. This homework, the reverse engineering homework, is due Wednesday at 4 p.m. After that, at 4:30, we're moving on to memory errors. The first couple of memory errors lectures are already online. Please watch them. The other ones will be up tonight. See you on Wednesday.